Welcome to qnawire.
So in this problem, we'll be applying conservation of energy um, during the motion of the first ball. So before the ball hits the bar, we'll be applying conservation of energy to find out the velocity just before the impact. And we'll do the same thing for this, because when the bar hits this ball and this ball goes upwards, we'll again have we can use the conservation of energy. And we'll be applying conservation of angular momentum to the collision between the first ball and the bar. So first, let's apply the conservation of energy in this part. So let me actually mark three places so that it's easier to understand. So this is one where we're going to apply conservation of energy. Then during the impact, so let's say the ball is here, so this is part two, where we'll be applying angular momentum conservation. And part three, where this ball reaches a certain height, we'll be applying conservation of energy again. So in the first part, we'll have half of mv squared equals to mgy, where y is the distance from here to here. So this is the potential, this is where we have potential energy, but there's no kinetic energy. But when the ball reaches here, the y becomes 0, and all we have is the kinetic energy. So from there we get velocity as square root of g times y. Now in part 2, we'll be applying the conservation of angular momentum. Now for to do so, we'll take the axis at the center of the bar. So L1 is m times v times r, which is mass as in 5 kg. V is 15.34 meters per second. We get that from here. So 15.34 meters per second. And r is 2 meters. So L1, or the angular momentum before collision, is 153.4 kg meter squared per second. And immediately after the collision, the bar and both of the balls are rotating together. So after collision, L2 will be simply I total times omega, since they're all rotating together. And I total is going to be the moment of inertia of this bar, which is 1 over 12 ml squared, where L is the length of the bar, plus twice mr squared, where m is the mr squared is the individual moment of inertia for each ball. So this is mr squared, and this one is mr squared as well. So we add them together to get 2mr squared. And it turns out that if we plug in the numbers, we see that I total is 50.67 kg meter squared. And from the conservation of angular momentum, we see that L2 is equal to L1, and we know that L1 is 153.4 kg meter squared per second, and L2 is I total times omega. So from there, that's L1. So from there, omega will be L1, which is or L2, which is 153.4 kg meter squared per second, divided by I total, which we figured out. So kg meter squared per second, and I total is 50.67 kg meter squared. And from there, omega becomes 3.027 radians per second. Right. So now we know the angular velocity. So we can easily say that v for the second ball, just after the collision, the second ball will have a linear speed, which is v, and that must be equal to r times omega. So which is 2 meters times 3.027 radians per second, and that gives us 6.055 meters per second. And this is moving upwards, so we can apply, now we can use this part 3 where we'll be applying conservation of energy again, where initially the ball will have, let's say, half mv squared as in kinetic energy, and if it reaches height h, then it will have a potential energy mgy, and from there y should be equal to 1.87 meters. So that's the height that the second ball will reach after the collision. Thank you.